Hey, calculus students. Let's take a look at some related rates problems. I'm not sure, is this assignment 75, 76? It's 74. Here's assignment 74, um, related rates problems, and I thought we could just look at some archetype problems. So these all deal with spheres. Okay, first one says find the rate at which the surface area is changing when r is 3 and dr dt is 4 centimeters per second. So we want to find the rate at which the surface area is changing when r equals 3 and dr dt equals 4 centimeters per second. So I would encourage you to think about how you could name um, this calculusly. The rate at which the surface area, and if you prefer A for area, that's fine with me. The rate at which the surface area is changing. Well, I see here a dr dt. That's the rate at which the radius is changing with respect to time. See, change in radius with respect to time. And so I want to do something similar for the rate at which area is changing. So I'm going to go with dA dt is what we're looking for. Now, this is called related rates because we have this rate and we want to relate it to this rate. And I think that means for us that what we need to do is imagine some sort of link between radius and surface area for spheres. And then if we find that link, we could just take the derivative of that thing with respect to time. Conveniently, we learned in geometry that 4 pi r squared was the surface area of a sphere. So, okay, if I come and I take the derivative here, there's a constant, this raised to that power, so I'm going to have 2 times 4 pi times, leave the inside alone, times the derivative of the inside with respect to time, dt. And on the other side, we're taking the derivative of area with respect to time. So dA dt. Great. And we know dr dt, we know r. Well, let's plug stuff in. So I'm going to have 8 pi times 3 times 4, and I'm going to end up with 24 times 4, 96 pi as my dA dt. And think about the units on this. 96 pi what? Well, area isn't centimeters. Area is centimeters times centimeters. So we want centimeters squared per second. Because these are seconds, these will be seconds. Okay? All right. Next one. How about find the rate of change in the radius of the sphere when radius equals 5 centimeters and volume is changing at a rate of 100 pi centimeters cubed per second. Okay, so how do you name these things calculusly? What is the rate of change in the radius? Well, I like dr dt for that, and that seems to be the thing we're looking for. And then here I see volume is changing at a rate of 100 pi. How can we name that? That's right. dv dt, and that's going to be 100 pi centimeters cubed per second. And so the change in volume over the change in time. Do we know a relationship between radius and volume that we can take the derivative of? Sure. We know that the volume of a sphere is 4/3 pi r cubed. Excellent. And now we want to take the derivative of both sides with respect to time. So we're going to have dv dt. And over here, we get 4 pi r squared. Don't forget to come back and take the derivative of that inside function, right? You took the derivative of the outside. That's why that 3 came down and canceled with that 3, and that's why we subtracted 1 and had that 2. But we still need to take the derivative of that inside with respect to time. Well, let's plug in what we know. We've got 100 pi over here, and we know the radius is 5, not 0.5, just 5. 4 pi, 5 squared, dr dt. Well, 5 squared is 25, times 4 is 100, times pi is 100 pi. Wasn't that interesting? So what happens there? Well, it looks to me like dr dt equals 1. The units, remember, 1 centimeter per second. Okay? You could read it this way and say that the radius is changing at 1 centimeter for every 1 second as well. Okay, so that's spheres. Now, what about cylinders? Cylinders and cones are much more common. Cylinders. Find the rate of change in volume when radius is 3 centimeters and height is 12 centimeters and lots of ands here, sorry about that. Height is changing at a rate of 8 centimeters per hour. Okay, so I guess we've got volume, change in volume. So I'm looking for dv dt. When radius is 3, when height is 12, and height is changing at a rate of 8. So now we've got the h dt equals 8. So do we know a relationship between these three things? Well, it turns out that the formula for volume of a cylinder is pi r squared h. So please, when we go through these formulas, if they don't come very quickly back to mind, you should probably write them down and make sure you're comfortable with them. So we're looking for dv dt, which means we need to take the derivative here. But I really don't want to take the derivative with respect to two different variables. I mean, I can, but that's going to introduce the concept of a dr dt, and we're not looking for a dr dt, and I don't have a dr dt. So I don't want to take this derivative with both of these here. And more specifically, I have a dh dt, and I don't have a dr dt. So I need to get rid of r and replace r with some stuff. Oh, wait. In a cylinder, as the level increases, is the radius changing? No. In a cylinder, the radius is a constant. So as the height is changing, the radius is not changing. Now, there are some of you who really want the honors AP Calc class, and that's the one that says, well, Mr. Kuka, at the very beginning, there's only one dot as you fill it, and then it goes all the way out here until we get here, and then it's a constant. Yeah, and those people are right too, but no, we're not in that class, so don't worry about that here. We're just going to say that this radius is a constant. So I'm going to take this radius in and plug it in now. Remember, we plug in constants before we take the derivative and changing quantities after we take the derivative. So this is going to be v equals pi times 3 squared h, or v equals 9 pi h. And now I want to take the derivative of both sides with respect to time. So I'll have dv dt over here, and here I have a constant times the derivative of height with respect to time. Well, we're looking for dv dt, and we know that dh dt is 8. So we've got 9 pi times 8, or 72 pi. Don't forget the units. Volume will be centimeters cubed, and time is hours. Yes, that's right. We didn't need this piece of information. Surprise! Yeah, okay. Number 4. Number 4 says, find the rate of change. Find the rate of change in no, that was 3. Find the rate of change in height of the cylinder when r equals 3, h equals 4, let's have these be inches, and volume is changing at a rate of 36 pi inches cubed per minute. All right, so do we know a relationship between height and radius and volume for a cylinder? We just did that. Pi r squared h. Find the rate of change in the height. We're looking for, good, dh dt, and the volume is changing at a rate of, so we know that dv dt is 36 pi. We know that r equals 3 and h equals 4. Okay. Again, I don't have any dr dt, so I don't really want to take the derivative of this while there's still an r here, and it's still a cylinder. So r is really still just a constant. I can plug that number in right now. And I would have no, I wouldn't. I would have v equals 9 pi h, and now we get that dv dt equals 9 pi dh dt. We plug in our dv dt, 36 pi, 9 pi, and we divide by 9 pi to get dh dt equals 4. And what are the units? Well, height is inches, and time is minutes. Okay, let's take a quick look at what would happen if we didn't plug this in as a constant right away. What could we still do this problem? So yeah, I think we can. Let's take a look. So I see a product here, right? So I'm going to take the derivative using the product rule. I'm going to have dv dt equals that times the derivative of this with respect to time, pi r squared times dh dt, plus I'm going to have that times the derivative of r squared with respect to time. So I'm going to have pi h times 2r. Don't forget to take the derivative with respect to time. All right, so over here we plug in our radius, which is 3. We've got pi 3 squared dh dt, and that's what we're looking for, plus pi, we know the height is 4, we know radius is 3, and dr dt. And that's kind of where we get stuck. And what you have to realize, if you've taken this path, is that, in fact, the radius is a constant 3. And so what's the rate of change of a constant? 0. Yeah, that's hard for a lot of people to do on a test. And lo and behold, here, we're going to get that same answer that we got before just by doing the substitution. And we're not going to have to worry about making this connection. But we can. I just think it's a longer road and wouldn't necessarily recommend it. Okay. More common even than cylinders in the last 2 decades on the AAP exam has been cones. Cones are very popular. The volume of a cone is changing at a rate of 24 pi cubed centimeters cubed per minute. So we think we can say dV dt is 24 pi centimeters cubed per minute. Given the radius is always equal to that of the height, so they're telling me that r and h are equal to each other. Find the rate of change in the height with respect to time. Oh, so they're looking for dh dt. Okay. When h equals 2. Okay, so first, do we know some sort of relationship between volume, radius, height for cone? Yes, yes we do. We learned that 1/3 pi r squared h is the formula for volume of a cone. And again, I'd kind of like to take this derivative with respect to only one thing over here, not two. I'm looking for dh dt. So I don't want to get rid of h. I want to get rid of r. Now r is changing. Now if we've got this cone, we can see here r, h, and then, sorry, there we go, 2 and 2. So we've got this sort of thing going on, where we can make a relationship between those values that we were given and also these general quantities. But for now, I see I'm looking for dh dt. That means I want to get rid of r, and I know that r equals h. Okay, so no, don't plug a 2 in because you haven't taken the derivative yet. Changing quantities, right? The radius is not the same radius. The height is not the same height. These are both changing quantities. So I can't plug a number in for these changing quantities until after I take the derivative with respect to time. Instead, what I'm going to do is I'm just going to make a simple substitution where I see the letter r, I'm going to put the letter h. I see the letter r, so I'm going to have 1/3 pi h squared times h, or pi over 3 h to the third. So there's my equation that I want to take the derivative of with respect to time. On the left-hand side, I'm going to have dV dt. On the right-hand side, bring down that 3. That'll cancel with the 3 on the bottom, so I get pi. Don't forget to subtract 1, h squared. And don't forget to take the derivative of that inside with respect to t. So what do we know? We know h is 2. 2 squared pi. We're looking for dh dt. And we know dV dt is 24 pi. So this is 4 pi. If we divide both sides by 4 pi, we get that dh dt is going to be 6. Now, what are the units on 6? Well, these are centimeters cubed per minute. This is a change in height, so that's centimeters per minute. Okay? Don't forget to ask questions about these if you have them, and certainly feel free to watch the video as much as you need. Number 6. Find the rate of change in the volume of a cone where radius is always not equal to height, but always 1/2 the height, given change in height is 6 feet per second when h equals 1 foot. Okay, what are we looking for? We're looking for dv dt. We know that radius is always half the height, r equals 1/2 h. That looks like a helping equation. And the change in height is 6. So they've told me that dh dt equals 6. Okay, and when h equals 1, but height isn't a constant in this problem, so I'm not going to be plugging in this 1 until after I take the derivative. This, though, is something I'm going to use, and again, I'm looking for dh dt, not dr dt. If I was looking for dr dt, I'd get rid of h, and I'd say, hey, h is equal to 2r. Why 2r? Well, I've got h by itself by multiplying both sides by 2. So I could get rid of h and have only r's if I made this substitution. Okay, so we know that volume of a cone is 1/3 pi r squared h. We know the radius is half a height, so v equals 1/3 pi 1/2 height squared times height. Well, when I square 1/2, I do not get 1. It's a very common mistake in this problem at this point for people to say, oh, that's going to be 1. 1/2 times 1/2 is 1/4 times h squared times h. Ooh, and I have that 1/4 times that 1/3. So I'm actually going to have pi over 12 h to the third. Here's my volume, right? Because h squared times h made that. 1/2 squared is 1/4 times 1/3 gives me that 12 in the denominator with a pi riding along on top. Hi pi, wave to pi as it goes by. And now let's take the derivative with respect to time on both sides. I want the derivative with respect to time. On the left-hand side, we're going to have dv dt. But what about on the right-hand side? dv dt. Well, on the right-hand side, I'm going to bring down that 3. I'll do some canceling. That'll give me pi over 4h. Don't forget, you brought down the 3, you subtracted 1. This is a 2 now. And now you come back and take the derivative of that inside with respect to time. Okay? So let's plug in what we know. Remember, we're looking for dv dt. We know that dh dt is 6. We know that height is 1. And dv dt. So it looks like 6 over 4. We could do some canceling. And dv dt is going to be 3 pi over 2. And these were centimeters per, rate of change, height is 1. Oh, feet, sorry. Feet per second. Okay. Volume, feet cubed. That's better. Okay, 7. 7 says, given twice the radius of a cone is equal to 5 times its height. That's going to be an interesting helping equation, isn't it? Find the rate of change in volume Are you getting to that place where at this point you don't want me to write the words, you just want me to write dv dt because you understand that You're going to name those words calculously as dv dt anyway. Okay, find the rate of change in volume when rate of change in radius is 7 feet per second and r equals 5 feet. All right, well, what are we looking for? Find the rate of change in volume. What's dv dt? I don't know. But we're given the rate of change in the radius. We know that dr dt equals 7 and r equals 5. Hey, I don't see any height information. Oh, twice the radius is equal to 5 times the height. Twice the radius is equal to 5 times the height. Now, do I want to solve this equation for r or for h? And my experience is a lot of students say we want to do this for r. So, well, let's just take a look at what happens. We get r equals 5 halves h, and we look over here, volume equals 1/3 pi r squared h, and we plug in for r, and now we've got 1 pi over 3, 5 halves h squared times h. So I'm going to have v equals 25 pi over 12, because that's 4 times 3 is 12, and h to the third. Now, when I go to take the derivative of this, sorry, I don't have h or dh dt. Now, I guess I could find h by using this little equation here. Yeah, I could plug in my radius and then solve for h. I have no way of finding dh dt though. So, no, I don't want to solve for that. I don't want to solve this equation for r. See how I have the information about r? That means I want to solve for the other one. So I want to solve this equation so that it says h equals 2/5 r. So now when I look at volume is 1/3 pi r squared height, I'm going to replace height with 2/5 r. So v equals 1/3 pi r squared times 2/5 r. Well, let's tidy this up a little bit. R squared times r is r to the third. 3 times 5 is 15 with a 2 pi on top. So volume is going to be 2 pi over 15 r to the third. And now we want to take the derivative of both sides here with respect to time. So I'll bring down that 3, and there'll be some canceling. I'll get 2 pi over 5 r squared. Don't forget to come back and take the derivative of the inside r with respect to time. And what was that giving us? That's right, the derivative with respect to time and volume. So change in volume with respect to time is going to be this. We know that dr dt is 7, so I'm putting a 7 there. We know that radius is 5, so I'm putting a 5 there. So we're going to have dv dt equals 2 pi over 5 times radius 5 squared times dr dt 7. Well, I can cancel one of those 5's, and I'm going to have 10 times 7 for 70 pi. And what were my units? Well, I had feet per second. Since this is volume, this is going to be cubic feet per second. That's a lot of cubic feet every second, if you ask me. Okay, so we've done cones. We've done cones. Let's take a look at some intersection problems. We talked about intersections before, and remember, what was the thing we need to remember as we go toward the intersection versus as we go away from the intersection? Okay, so rates are negative as we head toward the intersection. And rates are positive as we head away. So it's going to be very important for us to pay attention to, am I heading toward an intersection or am I going away? So for example, here we're heading south to the intersection. Once we've reached the intersection and gone out the other side, now we're still headed south, but up here, my rate is going to be negative because I'm heading toward the intersection. And down here, once I pass the intersection, yeah, my rate is going to be now positive. So we do need to pay attention to our location. All right. In these problems, I seem to have some ladders for you. Nope, I have an intersection as well. All right, so we've got a ladder. How fast is the 13-foot ladder? How fast is a 13-foot ladder sliding down the wall? If it is sliding out away from the wall at a rate of 8 feet per second. When the ladder is 12 feet from the wall. Okay, so I think I kind of want to understand this visually first. I've got a ladder. It's leaning up against a wall. Now, I know the ladder is 13 feet. By the way, is that a constant or is that a changing quantity? I mean, as the ladder slides down this wall, does the ladder length change from 13 feet? No, the ladder length doesn't change. This is a constant, and therefore I should plug that in before I take the derivative. All right? So that's good. And oh, they said sliding out away from the wall. Okay, let's call that x. We know that the rate at which we're sliding away from the wall is 8 feet per second. We want to know how fast it's sliding down the wall, so we want dw dt. And I'm calling that w. And do we have a relationship between these objects? Well, yeah. We've got Pythagorean theorem. X squared plus w squared equals L squared. Now, you can forget that this is a constant and take the derivative and have 2x dx dt plus 2w dw dt equals 2L dL dt. But if you take this path, you have to come up with a dL dt, which means you have to look at this and say, what is the change in the ladder length with respect to time? And ideally, you say the ladder isn't changing its length, and so that has to be a 0. If you don't do that, it's going to be a problem. Many students find it easier to plug the constant in before they take the derivative. So we're going to have x squared plus w squared equals 13 squared, or 169. Now, when I come and take the derivative here with respect to time, I do get 2x dx dt plus 2w dw dt equals the derivative of a constant is 0. Yes, we can divide everywhere by 2. And now, can we plug in what we know? Well, I know dx dt is 8. And no, there's no place there. I'm looking for that. But what about these? When the ladder is 12 feet from the wall. Oh, 12 feet from the wall. So this is 12. I can plug a 12 in here. But what about w? I still need w. Oh, right. This is the Pythagorean theorem problem. We know two of the sides. We're looking for the third. 12 squared plus w squared equals 13 squared. Hey, wasn't there a something 12, 13 right triangle? One of our Pythagorean triples? Yes, there was. There was 5, 12, 13. So we get w squared equals 25, and so w equals 5. So I'm going to plug in a w there of 5. I'm going to have 96 plus 5 dw dt equals 0. Subtract 96, divide by 5, I get dw dt equals negative 96 over 5. And our units here are feet per second. Um, is it reasonable that this rate is negative? Well, look, the ladder is sliding down towards the intersection. So yeah, I'm very happy about that negative there. Yay, negative. Okay, good. Let's do one last problem in this video, and we'll finish out the set with our next video. Here we're going to talk about a bicycle is west of an intersection, 12 feet west of the intersection. Remember, north, south, east, and west. Okay, bike is 12 feet west, so B equals 12 feet. And heading east, we're going that way with our bike, dB dt, heading east at a rate of 18 feet per second. Okay. Another bike is 9 feet south of the same intersection. I'm going to go with S because I already used B. Another bike is 9 feet. S equals 9. Heading south. So ds dt, we're heading this way. Heading south at a rate of 10 feet per second. Okay. Find the rate of change. Oh, how fast is the distance between them changing at this moment? Okay, and so we're looking for that. We're looking for the rate of change in the distance with respect to time. Well, again, I'm seeing a Pythagorean theorem problem. I've been given stuff about this, and I'm looking for the rate of change in that. All right, so that's going to be what? That's going to be b squared plus s squared equals d squared. And I can take the derivative here with respect to time. I'm going to have 2b db dt plus 2s ds dt equals 2d dd dt. Gosh, that's tiny and squished. Do you mind if I write it again? 2b db dt plus 2s ds dt equals 2d dd dt. Great. Now, we're looking for what? We're looking for this. We're looking for this. And because we're looking for this, we must know this, 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 and this. That's a lot of things to know. Well, how are we doing? Do we know those things? Well, we know the bike is 12. And yes, again, you can take out all those 2's. The bike is 12. dB dt is 18. But let's think about that. Positive 18 or negative 18? Well, the bike rider is heading toward the intersection, so dB dt is negative 18. Plus s, which is 9, times ds dt. Well, the bike is going away from the intersection here, and so that's going to be a positive 10. Equals d. Do we know d? I don't have a d. How can I find d? Well, remember we know b, and we know s, and we know that this is a Pythagorean theorem situation. This is 12, this is 9, and this is d. Ideally, you recognize this as 3 times 3, 3 times 4, 3, 4, 5 times 3, 4, 15, right triangle. But you could always just use the Pythagorean theorem and find d that way. And so I'm going to put a 15 here, and I have d dt. So 10 would be negative 180. 2 would be negative 36. So it's negative 216 plus 90. And then I'm going to divide by 15. But let's take care of this first. That's going to be negative 126 over 15. How about some units? We're going to have feet per second equals d dt. Great. And yes, I could divide by 3, but no, I'm not going to. Instead, I'm going to say, please let me know if you have any questions on these, and I can't wait to do some more problems with you. All right, take care, everyone.